Plaque of Appreciation, Professor Moungi G.Bawendi. In appreciation of your plenary lecture given at the 136th General Meeting of the Korean Chemical Society, I hereby present you this plaque on behalf of the Korean Chemical Society. Phil Ho Lee, President of KCS. 큰 박수 부탁드리겠습니다. 네, 기조강연의 사회는 우리 바웬디 교수님의 제자이신 포스텍의 김성지 회원께서 맡아주시겠습니다. 그러면 김성지 교수님 부탁드리겠습니다. please. 이렇게.
Good afternoon. I'm Seungji Kim from Postec. It is my great honor to introduce Professor Moungi G.Bawendi, the Lester Wolf Professor at MIT and 2023 Nobel Laureate in Chemistry. I would like to express my sincere gratitude to Professor Bawendi for traveling all the way to Changwon to join us for the Korean Chemical Society meeting today. I also wish to acknowledge the most unselfish efforts of organizers, including KCS President Phil Lee, Vice President Seung-Hoon Lee, and former Vice President Jae Young-sung, whose dedication and support made Professor Bawendi's presence here today possible. I hope this precious occasion with Professor Bawendi will inspire many young chemists in Korea, and that we may one day see future Nobel laureates emerge from among them. Thank you very much. Please join me in welcoming Professor Bawendi.
Thank you very much, Seungji, for the kind introduction. And I'm very pleased to be here today to tell you about the story of the discovery and the evolution of the science of quantum dots. Quantum dots are small particles that show interesting effects, and they were really one of the first nanomaterials that was engineered purposefully, and they have served as a model of the kind of science and materials characterization that you can do with many kinds of nanoparticles. So really the story is specifically about quantum dots, but it's more generally about the field of nanomaterials, about the kinds of things that you look for and that you can do with nanomaterials. So let me start this story. The story is also one about the importance of curiosity in science and research, and the one of time, because research takes time. So what I want you to come out of this is a timeline of going from the initial observation of an effect to widespread technological impact. Today, quantum dots are made in factories, in 5,000-liter reactors, in huge quantities, and they're all around us in displays. But the timeline is not fast, and that's another thing I want you to come out of this. Here we go. Let me first tell you a little bit about myself. I was born in Paris, in France. My mother is French and my father was Tunisian. Tunisia is a little country in North Africa. And as a child, my parents moved back and forth between Paris and Tunis. Two different cultures. Both spoke French. And eventually, after a little brief stay in Nice, in France also, we ended up in the US, in West Lafayette, Indiana, in the middle of the Midwest in the US. Here I am as a young child in one of my many trips between Paris and Tunis. And here I am in the airport in Paris, getting ready to go to the US for the first time. I was 10 years old, and I didn't know any English at all. My mother had tried to get me to learn some English, but I really didn't believe her when I was 10 that nobody spoke French in the US. And so it was a shock when I came to the middle of the country in the US, in West Lafayette, and the first child to come across the street to play with me spoke this really strange language, and I had no idea what he was saying. The body motions were different. You know, he came up to me and said, "Hi," and I had no idea what that motion meant. So I was very lost. But I was used to being lost because I had been going from Paris to Tunis many times. So it didn't completely destroy me. It took me about 6 months to learn English, and then, you know, when you're 10 years old, you learn languages quite quickly. So I was fluent after 6 months. The West Lafayette is the hometown of a university called Purdue University. Purdue University, if you replace, it's P-U-R-D-U-E. If you replace the first U with the letter E, in France, that means perdu, and perdu in French means lost. And so it was very appropriate for me to have ended up at Purdue. But why am I telling you this? Because my background, I think, informed a little bit about my science, about how I do science, and because I became very comfortable not fitting in, being an outsider. It didn't bother me to be an outsider because that was just the way it was for me. I didn't know anything different. I wasn't used to being part of a community and having grown up, you know, part of a tight-knit community. I was just happy being an outsider and basically being a little bit of an inner connected person. Okay, so that's my story, and then something the slides are not the right format, but that's okay. So then I went to Harvard University, and coming from the Midwest to the East Coast at the time, I was also lost because the culture of the East Coast was very different from the culture of the Midwest. And in fact, I was lost even in the schooling because the first exam that I took in chemistry in November or October of my first year, I failed it. I got 21 out of 100. It was the lowest grade in the class, and I was sure that that was the end of my time at Harvard, that I was going to have to go back home. But I stayed, and I learned how to study, and then afterwards it was okay. But there was a big shock to me to have failed that first exam in chemistry. And I loved chemistry, so it was really painful. But then after that I went to the University of Chicago, and as a graduate student, I was a theorist. I did statistical mechanics and thermodynamics on polymers. I loved mathematics, but after 3 years of doing that, even though I was writing papers and I was reasonably successful, I realized that my brain wasn't quite suited to do theory. There were many things that I didn't understand about what I was doing, many concepts that I could do the math, but it didn't feel intuitive. And so I decided to change fields. I changed fields to become an experimentalist. I wanted to work with real and see data appear, and I became a small molecule spectroscopist. I studied small molecular ions that were of interest to interstellar space. And I loved that because it was quantum mechanics. It was very basic quantum mechanics, and I loved quantum mechanics immediately. And one of the ions that I studied was H3+. It's the smallest polyatomic molecule that you can think of. It has 3 protons and 2 electrons. It can't be any smaller than that and be a polyatomic, bigger than a diatomic. And I studied its vibrational properties, its low vibrational properties in the infrared. And my work was then used in the 1990s when there was a comet that broke in pieces in the solar system, in 3 pieces. And these 3 pieces impacted Jupiter. There were 3 big explosions on Jupiter when the comet collided with Jupiter. And Jupiter is mostly made of hydrogen, the atmosphere. It's a big hydrogen ball. And the force of the explosion created a lot of H3+. And you could observe then the spectroscopy of H3+ from Earth. And my study of H3+ was then used to calculate the temperature of the explosion through the vibrational progression. And that was very satisfying, to have something that was really fundamental, that was driven by my curiosity of what made that molecule exist and do its thing, to have it actually be useful for something. As a graduate student, I spent a summer at Bell Laboratories working for Lou Bruce, and I discovered the world of condensed matter physics and condensed matter chemistry and visible lasers. And I thought I had come to heaven. Bell Labs was an amazing place. And I was first introduced to quantum dots during that time, in the summer of 1987. And I knew then that I had found my field, this new field. And what I really liked about this new field when I first encountered it was that it was completely new. Nobody else was working on this. Nobody in the world, really, except for maybe a handful of people, maybe 2 or 3 people, were working on this it was in the United States and largely in the Soviet Union. And because I was used not to being part of a community, it was perfectly fine with me that there was no community because it was so new. And I know that many people thought that it was maybe not a good idea to go into a field where there was no community, because who were you going to talk to? Who were you going to get letters from, right? But to me, that was fine. Today, there's a huge community in Korea. There's a huge number of groups that work on nanoparticles of many different kinds, and quantum dots as well. And Samsung has a huge team working on quantum dots. So now we have a huge community working on it. But at the time, there was really nobody working on it. After Bell Labs, I went to MIT, and I continued working on quantum dots with my own group, including great students like Professor Moungi Kim here. Okay, let me start from the beginning then. What is a quantum dot? A quantum dot is a small particle of semiconductor, a nanometer-sized particle of semiconductor that has a few thousand atoms or so, and it shows quantum size effects. The electrons show quantum size effects. So let me tell you about the quantum part first. But how do we know that we've made a quantum dots? That we've made particles that are appropriately monodispersed, all the same size, with good crystal structures, etc. Well, we have to find tools to do that. And the world of science is that many discoveries are built on innovations in instrumentation. Instrumentation allows us to characterize us, to see things that we weren't able to see before. And the piece of equipment that has been fundamentally important for nanoscience are the electron microscopes, because they allow us to see below the diffraction of light using electrons to see objects that are in the nanometer range. And so there's one of my students here working on an electron microscope. This is an early one. Today's microscopes look like big boxes. They have no knobs except a computer screen, and you have to sit in a different room. So I kind of like these microscopes because I like to twist knobs, and really control them. And when you have a good sample, you can see it. You can see that you have a good sample, and then you can characterize it, and you know that all the particles are the same size, etc. So the electron microscope is one of these tools that has been extremely critical for the development of nanoscience and of nanoparticles in general. Okay, what about the quantum part? When we think of an electron, we often think of an electron in a wire or in a circuit. And in a wire in a circuit, that electron behaves like a little particle. One of the really critical fundamental aspects of quantum mechanics is that particles can also behave as waves. It's the particle-wave duality. And whether it's a particle or a wave depends on how you measure it, where it resides, whether it's in a macroscopic wire or whether it's within an atom or a molecule. Electrons in a molecule have wave-like properties. That's what creates the molecular bond, right? So when I take that electron and I stuff it in a nanometer-sized box, that electron no longer behaves like a particle. You can't think of that electron as moving around the box really fast. That electron now behaves as a wave. It fills the whole box at the same time, all the time. It's a wave. We call that a wave function, described by a wave function. And our nanoboxes are these quantum dots, are these small particles, where we create a single electron in them and we allow it to fill the whole box as a wave. So why is that interesting or important, this concept of that electron as a wave in a cavity? The electron is basically inside a cavity where the cavity is the particle. Because we know how waves behave in cavities. You know that through sound waves. You know that if you take a flute or a piccolo, that the pitch of the sound is different. The cavity of a flute is much bigger than a piccolo, and the bigger cavity creates sound waves that are lower pitched than that of the piccolo. So pitch depends on size of cavity. We know this also for organ pipes. The small organ pipes, blue here, have much higher pitched sound than the bigger ones. The intermediate ones are somewhere in between. And I've color-coded the pitch here in analogy with light, where blue light has a higher energy than red light, and it's kind of like sound in that way. Okay, so now we have our boxes, our nanoboxes, and if we can make our nanoboxes of different sizes, it's like changing the size of the cavity. So in order to see the effect of the electron in different size cavities, we have to be able to put a single electron freely, to be free in that box. There are already thousands and thousands of electrons in these boxes because each atom in the box contains many, many electrons tied to the nucleus. But we're not interested in those electrons. Those electrons are localized right next to the nucleus. We want to have an electron that's free to explore the entire box. And the way we do that is by shining light and create an excitation. So we take blue light, in the case of this material, cadmium selenide, for instance, and that blue light, the energy of the blue light is enough to liberate one electron from being around an atom and free it to occupy the entire box. And that's how we create that electron. And now we have an electron in a cavity. Eventually, that electron in the cavity finds where it came from, goes back to the atom where it was from originally, and releases the energy as light. And the light that we see then informs us on the size of the cavity, the energy of that electron inside the cavity. So the bigger particles emit light of lower energy than the smaller particles, and that reflects the size of the cavity of the box. Now, the size of the cavity isn't everything, because there are atoms inside the cavity. So it's the size of the cavity and also the material that's inside the cavity that provides differences in energy for that electron. For instance, keeping with the analogy of sound and musical instruments, if you look at a guitar strings or violin strings, they're all the same size, but they have different pitch. So you can have the same wavelength, the same wave on the different strings and have different pitch. The E string on a violin is a very thin steel string, very taut, and that gives you a much higher pitch than the G string, which is a very thick string, which is not as stretched as the E string. So the material also is important. So it's a combination of the size of the cavity and the material. You know, if you fill a flute with helium, the pitch that you will hear is different than you fill it with air. The density of the gas that's inside the flute also will give you a different pitch. Right? Okay, so now we go back to the discovery of the quantum dots and my contribution with my students, which was to create material that we can really study and evolve into a technology. Alexei Ekimov and Louis Bruce were awarded the Nobel Prize for the discovery of the quantum dots, so the quantum size effect. And both were driven to this discovery by curiosity of the world around them. Alexei Ekimov was interested in color in stained glass. It was already known that the red color was due to making gold particles small. If you take gold, it no longer looks yellow, it looks red. You can disperse it in glass. The Greeks did this, and you could have these beautiful red colors in glass with gold particles in it. Faraday understood this effect in the 1800s, and in fact some of his samples are still in the Cavendish Museum in Cambridge in the UK. And so Alexei took glass and he mixed with the glass different elements that he thought might contribute to the color of the glass. And he observed that depending on the size, even though he had only maybe one or two elements, let's say copper chloride in his glass, he observed that depending on the processing condition of the glass, he found different colors or different properties. And he realized that what he was observing was the quantum mechanical effect of these cavities. And he combined then small angle X-ray diffraction to find the size of the particles and correlated that with his observations and wrote a paper in 1981 in the Soviet literature with the first three words, quantum size effect. Lou Bruce, independently at Bell Labs in the US, there was an energy crisis, and that was the birth of the renewable energy laboratories in the US. And there was a feeling that maybe if you could arrange things correctly, you could use semiconductors and an electrolyte and do photochemistry and make fuel from sunlight, something that we're still interested in as a society. And there was a new tool that had been invented called the picosecond laser. And a picosecond laser allows you to measure the kinetics of electron transfer across boundaries. So he wasn't interested, his curiosity was, how fast does an electron go from being excited in the semiconductor to going into the liquid to do a reaction on molecules in the liquid? What was that transfer process? How fast was that? What was the kinetics of that electron transfer process? So he was using that new tool to study that. And in order to get better signal to noise, he needed more surface to volume area ratio. He needed a lot of surface because this was an interface problem. And in order to get a higher surface to volume ratio, you needed to make the particles smaller and smaller. And so he reached the limit, the nanosize limit, and was in that limit that he saw that depending on how he made his particles, they had different colors. he was at Bell Labs, and he had available to him electron microscopes, so he was able then to correlate the size of the particles that he saw in the electron microscope with the colors that he was seeing and measuring. And he wrote a paper in 1983 in the Western literature, in the US literature, with the first 3 words being quantum size effect. Then there are other words there because he was interested in the redox properties, so that's what the paper was about. Alexei and Louis didn't know about each other. They didn't know about each other. It took many years for them to actually realize that they were working on the same thing. In fact, it was Louis that first found the English translation from Russian of Alexei's paper, and then he wrote him a letter in the 1990s to introduce himself, to say, it looks like we're working on the same thing, you know, on both sides of the Iron Curtain. So I came in, I was a postdoc with Louis, and so I started working on quantum dots in the late 1980s. 87 is when I started. And the state of quantum dots back then was that they were made at room temperature in water-based chemistry. The quality of the material was good enough that you could observe this quantum size effect. But it wasn't good enough to do real physics on it, because at room temperature, the crystal was not crystalline, and it was full of defects. The surface of the crystal was oxidized because it was made in water. And so you had little particles that were very strange shapes with oxidized surfaces, full of defects, and you could see the change in color, but you really couldn't interrogate it to really understand what my curiosity was, which was, how do the properties change when you go from the molecular scale to the bulk scale? A silicon atom is nothing like a solid piece of silicon. So somewhere along the way, the properties of bulk silicon begin to appear. How does that work? Where do they come in? How do the different properties appear? Some will appear earlier than others. The crystal structure may only need a few thousand atoms. But if you're looking at some more delocalized properties, maybe you'll need 10,000 atoms. So how does property and size come together to create the bulk material? That was my curiosity. And I needed good samples in order to do that. And that was my contribution at MIT with my students. And this is the paper on the synthesis of quantum dots, which then allowed us to do physics on the material. It eventually allowed the material to become a technology that was the synthesis part of the quantum of the Nobel Prize. So let me tell you about that. So when I was at Bell Labs, I had discovered that you could take these water-based particles, which were really quite defective and not very good, and you could disperse them in a solvent, a high-temperature solvent, and make them better. And the solvent that I chose was a phosphine oxide combination. And it worked mostly some of the time, but it didn't work all the time. There was a period at Bell Labs where for 4 months, my procedure didn't work at all. It kept failing. I didn't know why, but I called it magic. I didn't know why it didn't work some of the time. And when I came to MIT and I tried to reproduce what I had observed at Bell Labs, it never worked. The magic disappeared. And for the first 6 months at MIT, I kept doing the same thing over and over again, trying to make a sample that then I could try to study. And I kept failing. I had 2 wonderful students, Chris Murray and David Norris. I tell people the secret to success is to hire people that are smarter than you. And so I was very lucky with Chris Murray and David Norris. And so with both of them, then we decided that we needed to reinvent how we made particles. I knew from my time at Bell Labs that we needed to have high temperature. to have good crystal. And I knew that we needed to get rid of the water because we didn't want oxidation. I knew that we needed to do everything under inert atmosphere. The other thing that I had realized was that in order to make a monodisperse, or something that has a good size distribution, I had the feeling that you had to separate nucleation and growth, that you had to create little seeds, and then you could then grow on the seeds. And this was an idea that wasn't new. In the 1950s, Lemaire had described the growth of particles this way, from nucleation and growth. And so we needed to devise a process that had these three things: separately homogeneous nucleation followed by growth, high temperature, and air-free. And so we were physical chemists. So, you know, we weren't an organic chemist. So what we did was maybe a little strange if you were an inorganic chemist. But because I didn't know any better, and because I didn't care that I didn't know any better, because that was my background. You know, I wasn't part of a community, I just did things. And so we had metal organic precursors that were stable at room temperature, quickly injecting them in a high temperature solvent with ligands. The ligands bind to the surface of the particle to slow down its growth and prevent the growth from being catastrophically fast. When the metal organic precursors come into contact with a hot solvent, they break apart and they release the elements that are then made to make the particles. That's the nucleation part. Once you deplete the concentration, then you can no longer nucleate, and you start to grow on top of the seeds that you've created. That's the growth part. And because color is a function of size, it's very satisfying because you can see the process with your eyes. You can see quantum mechanics with your eyes as the particles grow, as the cavities get bigger. And we wrote a paper, this paper that was cited, this 1993 paper that was cited by the Nobel Committee. And there's a few words that I've underlined in this paper. This was my first paper as an assistant professor. So I started at MIT in 1990, and this was a paper we published in 93. And today, in my department, if an assistant professor doesn't write any papers for the first 3 years, we're a little worried. You know, we think, maybe things are not going so well, right? But it was very important for me that this paper that we wrote was a really good paper. I wanted to be really well characterized. I didn't want, as I told Chris Murray at one point, the world doesn't need another synthesis for bad quantum dots. What was the point of that? So in this paper, we have the words simple route and a single reaction. That turned out to be really important for commercialization eventually, because the cost of making anything depends on the number of steps. It doesn't matter what it is, if it's a car, if it's a semiconductor chip, whether it's a pharmaceutical drug. The more steps you need to make it, the more expensive it is to make. That doesn't mean it's more expensive to buy, it's more expensive to make, right? And so this meant that you could scale inexpensively. And the size-selective precipitation was a way to purify this nanomaterial. It was, you know, if you're a chemist, you run your sample through a column, you crystallize it, you find ways to purify your new product so you can characterize it. And so we also needed to do that. So that's the selective precipitation part. And after doing that, we're able to get samples that we were able then to do physics with it and really begin to understand this process of evolution from atom to bulk. And this is an example of a spectrum from that time. And the main peak at around 600 nanometers or so, that's that wave, that's the lowest energy wave, the fundamental wave in the cavity. Call that the exciton. Then you have a couple more peaks. Those extra peaks that you see are the harmonics of the fundamental. In music, you have, you know, many harmonics. So those are harmonics of that waves that's in that cavity that we're beginning to observe. Then you have emission, fluorescence. That's the single peak labeled fluorescence there. And that was kind of the first time that we saw light from these particles where the light was a single well-defined color, a color that was defined purely by the size of the box. Before that, if we saw any light coming from the particles, it was very broad white emission from defects with a quantum yield that approached 0. But here we had a quantum yield, the efficiency of the emission was around 15 to 20%. And to me, that was incredibly bright compared to what we had before. It was so much better than 0, right? And I was so happy with that. And then I mentioned that to one of my colleagues in Germany, Horst Weller, who was working on quantum dots at the time. And I said, these are amazing, they're so bright. And he said, well, 15 to 20% means that 80 to 90% of your material is crap. And he was right? So that was also a motivation then to get this 15% quantum efficiency and try to make it as high as possible. And thinking about it, there was really no reason why the quantum yield couldn't be 100%. From the basic physics of the material, it was just a matter of making the material better and to understand the interface of the material and the defects of the surface to try to prevent the electron from finding those defects and losing its energy there. The other thing that we were able to show, this is from Chris Murray's thesis, is the exquisite control that we had over the size of the particle. So on the left here, you see a series of absorptions. And the difference in, you see going from 400 nanometers on the bottom, these are about 1 or so nanometer sized particles. And then on the very top, at 15 nanometer particles, those are basically bulk-like spectra. And we see the trajectory as the particle size or the cavity gets bigger and bigger, the particles get redder and redder. And the difference in the number of atoms between any two of these spectra is not very many. It's a handful of atoms. And so just by picking the time to take the samples out, we could see that we could really control the size with exquisite control. And that allowed us then to study the fundamental and the relationship between the fundamental and the harmonics in the waves that the electron had in the cavity. This is the example of this synthesis. The flask is at 300 Celsius here. This video was taken in 2010. There's the seeds. The seeds are formed immediately after injection. And then there's going to be a slow growth. The process of making quantum dots today at scale, in manufacturing scale, is essentially the same process as this. It's this nucleation and growth at high temperature, and then you control it by time. So now the particles are much bigger, and then you can see the progression of color as a function of time. And then if you shine a UV light on it, then you see the faint emission that then depends on the size of the particle. The video on YouTube has a soundtrack to it that my students put to it back in 2010. It's a very exciting soundtrack. So if you want to hear that, you can go to YouTube and see it. So then when we had these beautiful samples, the first thing that we decided to do was to study the physics of them. And one of the things you can do then is to go to low temperature, 4 Kelvin or 10 Kelvin, cryogenic temperatures, and really begin to study how these harmonics depend on the size of the particle. So my x-axis here is basically size. I have it on top. On my left-hand side, your right-hand side are the small particles, and on the right-hand side, my right-hand side, your left, are the big particles. And what you see is, on the small particle side, you see all the energy of these harmonics. The harmonics all begin to come together as the particle gets bigger. And they do that continuously, uniformly, so monotonically, as if the particle is empty, as if there's nothing in there. It's just a big cavity with nothing inside. And then something happens at a certain size. The certain size where this thing called an avoided crossing happens. Spectroscopists, when they see an avoided crossing, they get very happy. And I was extremely excited when we saw that, because it meant that we were learning some fundamental physics. We were seeing something that was really important for the physics of the material. And it turns out that this part where the harmonics no longer behave like the particle, like the cavity is empty, it's where the electron begins to be aware that there are actually elements, there are actually atoms in the cavity. And it's scattering off these atoms, and it's seeing the spin-orbit coupling, it's seeing the extended crystal structure. And that crystal structure is what we see in the bulk material. And that's the spin-orbit coupling energy between 0 and 0.4 eV here that we see in the bulk material. So that's the first indication that we're beginning to see bulk properties happen. And that happens around 4 or 5 nanometers in size. Okay? It's not yet the bulk, but this is one of the properties that begins to appear when the particle gets big enough. Another thing that you see when you make very good samples is that when you dry them, the particles arrange themselves in a lattice, and like an artificial solid. And this was the beginning of thinking these are artificial atoms, and we can make artificial solids, and maybe they'll have interesting properties. Using small particles as a new periodic table and trying to create new solids with new properties. And they could be pretty large, and this is Sherry Kagan that worked on this. A big advance came in the 1990s, so remember, the discovery was in 1980, early 1980, 81, 82, 83. It took 10 years from that discovery for the synthesis to appear. Once we had good samples, then things went much faster. We were able to do physics on it, and this discovery of making core shell materials to really protect the quantum dot from the environment allowed the quantum yield to go up to 100%. And then we were able to begin to apply it. The first company that did the application was Quantum Dot Corporation in 1998, just 5 years after the publication of the paper of this paper. And the application was to use the particles in biology as fluorescent tags, because we thought these particles were much more robust than fluorescent dyes. And in fact, the red here are quantum dots, and the green is a fluorescent dye showing the difference in photobleaching. That turned out to be a very hard application, but we could do things that you couldn't do with dye molecules. This is another example where we went in vivo, and we worked very hard to put a coating of organics on the surface of the particles, ligands on the surface, to protect them from water. Because remember, these semiconductors, they don't like water. So if you're going to use them in a biological environment, you have to protect them. So the organic chemistry was just as important as the quantum dot itself. Then if you were looking into a mouse model, you can see that the red fluorescences from the dots, you can see it diffuse inside tissue without aggregating. And then you can do more complicated experiment. This is a multicolor experiment of looking at rare cells, these hematopoietic precursor cells, in vivo in an animal model. And our collaborators are then interested in studying the environment of these rare cells. We can inject red-emitting quantum dots and green-emitting quantum dots, and red and green together make yellow. And these special cells are the only ones that have receptors for both colors. Then in the microscope, you see the yellow cell, and you know this is the cell you're looking for. And you can start to study it. We can go in the infrared, where dyes don't emit light, but the quantum dots do. And we can look at it, for instance, in this case, this is a tumor in a mouse model. The red are the arteries, the blue are the veins, and the tumor here is in green. And then by using big composite 100 nanometer particles that emit in the infrared, we can follow the flow of blood in the tumor or in the healthy brain. And the difference that you can see tells you why it's so hard to treat solid tumors. Because in normal tissue, the blood flows freely and fast. When the tumor, these particles are not going anywhere. Some of the particles just go back and forth and back and forth. And you can really visualize then the problem of drug delivery directly in this case. The invention or the innovation that really made the particles a real technology beyond biology was the invention of the blue diode by Nakamura in the 1990s. Blue diodes that emit at 465 nanometers that have changed the world, really, changed lighting, and et cetera. And the particles, the quantum dots, are special because they can absorb light. Every size absorb at 465 nanometers. So by using one color LED, you can create all the different colors in emission. And so that application was in collaboration with electrical engineers. And we realized, and so there were two companies that were formed out of MIT and other places, Nanosys and Quantum Dot Corporation. And the first product was then these light bulbs. This was the beginning of LED lighting, where the light from the LED lights lacked some red. It was a blue diode with a yellow pigment on top, and it looked white, but if you looked at yourself in the mirror in the morning, you looked like a ghost. And you would just want to go back to bed because there wasn't enough red in the lighting. By putting quantum dots to take some of the blue light and emit red, then we were able to put a more beautiful white light, a warmer white light. The problem from a business perspective is that was okay when the light bulbs in 2010 cost $100. But you couldn't make a business out of it when the light bulbs cost $25 or less. And so it was a good technology, but not a financial success in that sense. The application that looks very much like the light bulb that ended up being the killer app was to use them in displays. So in displays, one of the first demonstrations was to use blue diodes, and then red and green emitting quantum dots, and then in the light in the light plane of this LCD display, you have RGB. All the colors, the only three colors that you need to make a color display. And the first company to do this was Sony, and they built these in the 2012 model year. They built these quantum dot displays, QD LED displays, these QD LCD displays. And they worked really well. They were over-engineered, and they got quantum dots from QD Vision. It was a great technology, but Sony dropped it after 1 year. And the reason why they dropped it is because QD Vision was a very small startup company, and they were able to make these glass-filled, these quantum dots filled inside these glass tubes, one at a time by hand. But when it came to scaling is also really hard, right? Going from making 1 unit by hand to making 1 million units in a factory, that's a hard thing to do. And they had promised Sony they would do that in 6 months, and they didn't make it. But Samsung saw that this was a great technology, and so they went ahead and they bought QD Vision, or at least the intellectual property. Most importantly, they bought the trademark, QLED. And the trademark was actually quite important because if you take the Q and get rid of this little tail on the Q, it looks like OLED, right? And LG was selling OLED TVs, so Samsung could say, we're better than LG because we have QLED TVs. So that trademark was also very valuable. And so they made the QLED TVs. They used indium phosphide as opposed to cat cyanide. So they spent a lot of time and a lot of money to develop indium phosphide quantum dots. And they're amazing quantum dots, and they've really been able to run with the technology. Today, the displays, the state-of-the-art displays are OLED, pixelated displays, blue OLED, and inkjet printed on the blue OLEDs are red and green emitting quantum dots, and that's how you get all the three colors. And you get the pure black of OLEDs, and you get the colors of the quantum dot at the same time. When Sony first started selling the QD LED displays, I asked them to give me a TV. because I had invented the quantum dots. You know, I thought, right, they should give me a TV, right? So I asked QD Vision to give, and QD Vision said, well, we can't give you one because Sony won't even give us one. And so I had to wait a few years until they were on sale on Amazon to buy my QD LED TVs. When the Nobel Prize was announced, you know, October 3rd, 2023, that afternoon, I got an email from Samsung Display asking me where I wanted my new TV and how big I wanted it to be. So I told them I want the biggest one possible, and you give it to me to my office. That's what a Nobel Prize does, you know. It gives you more cachet. Okay, let me tell you one more application before I finish. This is a fun application, but it's still the application of color conversion, where if you're looking at a camera that sees in the infrared, like a night vision camera is made with an indium gallium arsenide sensor. They can't see the UV, right? And so if you want to see the UV or the visible and the infrared at the same time, you need 2 or 3 cameras. But if you have quantum dots that absorb in the UV and emit in the infrared, you can coat the sensor with a thin layer of quantum dots, lead sulfide in this case here, and you can sensitize your camera to see in the UV. And let me show you what that looks like then. This is a movie or a scene that my students, Scott Geyer and my collaborator at Raytheon, Frank Jaworski, filmed. And here what they're doing is they're recreating a scene from maybe the 1960s in Berlin. You know, this is a spy scene. And these 2 spies here are trading suitcases, and one of them has secret documents in it. And there's another spy, maybe a Russian spy, that's put a little tag on the suitcase with the secret documents, and that tag emits in the UV to keep track of it. And he's trying to keep track of it using a night vision camera. And so half of the sensor is coated with dots, and you can see the tag in the UV. And on the other side of the red dotted line, there are no dots, right? And so as Frank then is standing up and carrying the secret document suitcase, you can see the difference between the dots and no dots. And you can see how dramatic you can sensitize then with a very simple addition of quantum dots. You can sensitize this thing. Okay, many more applications in flexible displays and photovoltaics, night vision cameras. So what have we created then? What's the state of today? So starting with quantum dots, one kind of material, the same idea of this nucleation and growth and really high quality characterization, this monodispersity, can be applied to many other materials, not just semiconductors, but also metals and semi-metals, magnetic materials, you name it. You can make small particles of almost anything, and then they have properties that can be either chemical properties or mechanical properties or physical properties that depend on the size. Today, we have many morphologies. We can make these things as cubes. We can make them chiral. We can make them into platelets. And we can assemble together. So really, the field, this community now, huge community, has created a new kind of chemistry, a chemistry of nanoparticles that can create new properties. And these new properties have been applied commercially in displays, in biomedical imaging, in light sensing, in solar energy, and there are many more applications that are being studied all over the world in catalysis, photocatalysis, in electronic optics, and in my case, my research now is into the quantum optics of these materials. I've had a lot of students, and I couldn't have done any of this without my students. Very smart students, 150 or so over the years. They're the ones that did all the work, and they're the ones that I have to thank for this. And I've been asked over since the last 2 years, to give advice to young scientists. So for the students here, it took me about 5 minutes to write this. It was like one day, I had to do this. So my advice, stay curious. Curiosity is the critical, important part to discovery. You can be the smartest person in the room, but if you have no curiosity, you'll never discover anything. Keep learning. Curiosity will make you want to learn. And the more you learn about the world around you and fields that are around what you're studying, the more you'll be able to make connections between your field and other fields and innovate between fields. But be flexible at the same time, because failure is part of research. You may have an idea and you pursue it, and at some point you're going to have to switch directions because it won't work. So you have to keep flexible and find your new directions. But don't give up. Just because you failed a few times just means you haven't gone into the right path. So don't give up. And finally, if you enjoy what you're doing, then you'll be happy and you're more likely to be successful. So enjoy life. There's only one. It's not a dress rehearsal. This is it. And thank you for listening to me.
Thank you.